Now let's understand instantaneous rate. In chemical kinetics, average rate is not much useful because it covers a large time interval during which the rate of reaction changes significantly. So to make it more useful, the time interval must be as small as possible. So in general, for change in concentration of any species, when limit delta t tends to 0, then delta x by delta t is equal to dx by dt. So whenever the change becomes very small value, so delta x we write it as dx and delta t we represent as dt. So dx by dt is nothing but equal to the rate of that chemical reaction. So here dx is infinitesimally small change in concentration corresponding to infinitesimally small change in time. So dt is this minute change in time interval and dx is the minute change of concentration in that minute time interval. In general, if dx represents very small change in concentration of any species during very small time interval change of dt, then we can write the rate of reaction like this. Rate of reaction is equal to dx by dt, where dx is the minute change of concentration in that minute time interval of dt, isn't it? So therefore we can define the instantaneous rate like this. The instantaneous rate of reaction is defined as the rate of change of concentration of any one of the reactant or product at that particular instant of time. As we are using a very minute time interval change, so we are using the term called at that particular instant of time. What is the change in concentration of any one of the reactant or product? That is called as instantaneous rate. Is it clear the difference between the average rate and instantaneous rate? In case of average rate, the rate is measured over a long time interval, and in case of instantaneous rate, the rate is measured over very minute or small time interval. That is the basic difference between average rate and instantaneous rate. Now let's consider an example where reactions involving different stoichiometric coefficients of reactants and products are involved. This example, nitrogen and oxygen combined in order to form nitric oxide. Now here the rate of reaction can be expressed in terms of nitrogen, in terms of oxygen, or even in terms of nitric oxide, and it is like this. The rate of disappearance of nitrogen, how we will write? That is equal to minus dN2 by dt, isn't it? Minus indicates that the concentration of nitrogen is decreasing along with the time, and this dN2 indicates the change in concentration and dt indicates the change in time interval. Then what will be the rate of disappearance of oxygen? And that is equal to minus dO2 by dt, because again oxygen is a reactant, so its concentration also decreases along with the time as that of nitrogen. So for both nitrogen and oxygen, we need to keep the negative sign in front of the expression. Then how we will write the expression for the rate of formation of nitric oxide? That is equal to plus dNO by dt, isn't it? As nitric oxide is a product, we need to keep the positive sign in front of the expression. So this is how we express the rate of each and every term separately. But from the balanced chemical equation, we know that 1 mole of nitrogen is combining with 1 mole of oxygen in order to give 2 moles of nitric oxide, isn't it? So this indicates that the rate at which nitrogen disappears is same as that of the rate at which oxygen disappears. Or in another way, the disappearance of both nitrogen and oxygen occurs at the same rate. But what is the case for the nitric oxide? the rate of appearance of nitric oxide is twice the rate of disappearance of this particular rate, isn't it? It's very clear from the equation that 1 mole of nitrogen combined with 1 mole of oxygen in order to get 2 moles of nitric oxide. So I can say that the rate of formation of nitric oxide is twice that of the rate of disappearance of nitrogen or the rate of disappearance of oxygen. But to get the unique value of the reaction rate, that is to make it independent of the concentration term chosen, what we need to do, we need to equate one rate with the other rate, because every time we cannot say that this is the rate in terms of nitrogen and this is the rate in terms of oxygen, rate in terms of nitric oxide. What we can say that this is the rate of the reaction in general. So when we equate this rate with the other rate, what we need to do is we need to make this rate into half so that it becomes equal to that of the rate of nitrogen and oxygen disappearance, isn't it? Because just now I mentioned that the rate of formation of nitric oxide is twice the rate of disappearance of nitrogen or that of the oxygen. So that is the reason why we can write like this. Rate of reaction is equal to minus dN2 by dt, which is equal to minus dO2 by dt, which is equal to half of dNO by dt. Why we are writing as half of dNO by dt? Because actually the rate of appearance of nitric oxide is twice the rate of disappearance of these two. And to get a unique value of the reaction rate independent of the concentration terms chosen, we need to equate all of this. Or in another way, we can write like this. Minus 2dN2 by dt minus 2dO2 by dt, which is equal to dNO by dt. So to make it very simple, while we are writing the rate of reaction in terms of any of the concentration species, we need to divide the rate of reaction defined with any of that reactant or product by the stoichiometric coefficient of that reactant or product involved in the reaction. Let me explain by taking another example. See here, 2 moles of hydrogen iodide are decomposed in order to get 1 mole of hydrogen and 1 mole of iodine. So here from the equation it is very clear that the rate of appearance of hydrogen and iodine will be definitely the same. But the rate of disappearance of Hi is twice that of these particular rates. So what we need to do in order to equate all these, we need to divide the rate of reaction in terms of hydrogen iodide by 2. So it becomes like this. Rate of reaction is equal to minus of half of dHi by dt, and which is equal to, no need to write the plus symbol, I am simply writing it as dH2 by dt, and which is equal to di2 by dt. Whatever is the coefficient present in front of the reactant, that will become 1 upon rate of reaction of that particular term upon that coefficient. Is it clear? Now let me write for a general reaction. For A moles of A combining with B moles of B in order to form C moles of C and D moles of D. How we will write the rate? Rate is equal to minus of 1 upon A dA by dt, which is equal to minus of 1 upon B dB by dt equal to plus 1 upon C dC by dt, which is equal to 1 upon D dd by dt. So that is how we write the rate of reaction for this general reaction.